It's now that we're recording. For the last quiz, I have a TA for the course because it's a large section class. And so what that means is they will mostly grade it. And they said that, or he said that he will have it done later today. So sorry about not getting it this morning. If you did not submit it through Blackboard and just emailed it to me, then I will grade it. So I grade some of them, he grades some of them. And if you want to see that one, since you didn't submit it through Blackboard, you'll send me an email. I'll send you back the graded quiz. And once he puts grades up for the rest of them, I'll put your grade up also. Once you do, general thing for quizzes is I have no problem with you arguing about points. So if you think too many points are taken off, especially if it's graded by the TA, send me an email. I'll download it so I can look at it. We'll talk about it. So if you have questions about the grading, you're going to send me an email at some point. So this week, we again will have a quiz on Thursday, so it'll work just like last week. So Wednesday, we'll have, as I said, in the middle, half hour where you'll get the quiz review. We'll go over it. Well, you'll try it on your own. We'll go over it. And then Thursday, again, the last hour or so will be time for the quiz. So we'll have about half an hour again of new material, stuff that is not on the quiz, and then the quiz. And then next week is our first test. Obviously, for that, it'll be different. That you'll get the review on Monday. Wednesday, we might do a little bit new, but probably not much at all. Most of the time, we'll just be going over questions on the test. And I'm not sure exactly how far it'll go, but it'll probably be chapters 1 and 2. It'll depend on how far we get. Okay. So today will be similar to most of the classes once we got going, which is we're going to start off with some of the homework. And then we'll move into 2.4, which we didn't complete. So start with homework from 2.3. I'm getting ahead of myself, 2.1. So really basic one, just here's a function. And we just want to take partial derivatives. I think it only asks for f of x and f of y, but let's also get one or more of the second order ones. And remember, the idea for this is, and when I take the derivative with respect to x, and I can either write that way or this way, where the symbol before the f and x is the partial symbol, which for me usually looks like a 2, but it's officially the partial symbol. And remember, the idea for that is we assume every other variable is a constant. So what is the derivative of this with respect to x? In some ways, it probably takes you longer to write than it is. So yes, what is the derivative of this with respect to x? And then we'll get the derivative with respect to y, and then at least one of the second orders. So 2xy plus 2y. Because we're assuming y is a constant, so we take the derivative of the x squared, we leave the y alone. The derivative with respect to y then would be actually very similar. And let's do a couple of the second order. So let's do the second derivative with both times with respect to x. So what would be that? So that would be obviously come out of this one. So the derivative again would be, right, nice and simple, because since y is a constant, if we're multiplying, it just stays there. But if it's by itself, derivative is 0. And let's do the next one. And remember, in this case, it doesn't matter which way, so it doesn't matter if we go from fx, where we then take the derivative with respect to y, or we start with fy and take the derivative with respect to x. So the order isn't going to matter. Although I think in the text they have somewhere doing it one way is much easier than doing it the other way. Here it should matter. So if I'm using this one, I get 2x plus 2 plus 2y. So here's a really basic one, just reminding you that the way you do partial derivatives is just the idea that you assume all the constants except for the one you're looking at are constants. So any questions on this? Okay. So another one. And this one, and you'll see why once I write it, I'm going to not write everything that's in the text. So it's one of these table ones. Could be, yeah, sure. In some, yes, we've now done a couple of them. I could certainly put it on. In some ways, I can see that you know how to do it the other way, which again, we're assuming that it's a constant. So let me ask the question before we start doing it. So in some ways, this is a check to see if you remember stuff from Calc 1, which is that the derivative, oops, I lost a piece, that the derivative is like the slope of a line. So I want to remind you that slope or instantaneous rate of change is the same as derivative. I don't put it on too many things because there are few possible answers, so it is a bit of a pain to grade, although not too terrible. So I could ask you for something like this. So if I want to find the derivative of the function with respect to x at the given point, then here what I'm checking is that you know that it's, again, the idea is we're assuming y is a constant, which means we're assuming y is definitely in this row, so y is not changing. That reduces it to a one-dimensional thing, and so we can use the slope from Calc 1. So give me, what is one estimate? Because given these numbers, there are kind of three possible estimates you could use. Right, so the change in y, although you don't really want to use y. So right, so one of them could be 1.968 minus, except careful, not the 2.624, but b. Right, so if we were doing that, it would be the Right, so the change in the function over the change in x. Didn't explicitly label, but that's by default. That needs to be x. It's right there. Right, it's because we're assuming, since we're doing the derivative with respect to x, we're assuming y is 1.2. Oh, that's a yeah, that's a 2.4. Sorry about that. And whatever that number is. And then going the other way, now we're assuming x the constant. So we're doing the column instead. And we have a couple choices. I might as well be consistent. Again, the change in the function over the change in this case of y. So we're doing the derivative with respect to y. So I might do one just, as I said, kind of a check. This is kind of really explicitly making you use the fact that when you take the derivative with respect to x, you're assuming y is a constant. So that lets you know whether you're using a row or a column. And also checking, see if you remember that derivative is the same as the slope, which means the change in the function over the change in the variable you're looking at. So we're kind of going backwards. In Calc 1, we would have started with this type of one and gone to previous one, but here we go backwards. So just kind of as a check. Yeah, so I said in some ways there are three possibilities in some ways for fx. So I went, for this one, we went from -1 to -0.8, but we could just easily do the and enough room, I could also go from the -1 to the -0.6. And any of those would be okay. Yes, they'll get slightly different numbers because they're all estimates, but for us, any of them would be okay. Actually, I've just changed things. So let me ask again. Any problems hearing me? Can you still hear me? I guess is the question. Yes, because I'm in my apartment and I think outside they're going to start cutting some things down, and so I plugged in, so hopefully you won't hear it quite as. All right, so second one. Third one I was going to do is pretty much the same as one. Just slightly more complicated, reminding you that pretty much all the rules you had for Calc 1 for derivatives still apply. And in this text, he likes changing the names of the variables. If you want to change everything into x's and y's, that's fine. He likes using a's and b's and then s's and t's and u's and w's and x1s and x2s, emphasizing the fact that the name of the variable doesn't matter. But if you're more comfortable with other names, that's fine. So here we want to take the derivative with respect to x1. I lost the 1. So what rule do we need to get this one? I think we did one of these last Wednesday. All right, so I need a product rule. So therefore, I'm going to do something such as take the derivative of x1 squared natural log alone and leave the x1 squared alone and take the derivative of the natural log. In this case, we don't need the chain rule because the derivative of the inside, the derivative of x1 plus x2 is 1. Why don't I put that, just emphasize that we could also have chain rule stuff. Little thing, I think I said this last week. In general, for these types of things, unless you're going to be using it for something else, once you have an answer, you do not have to simplify. So leaving it in that form would be fun, especially because, in this case, we're going to be plugging in a number, and we're going to just get a single number anyway. So first one is 0, because natural log of 1. Second one, you get the 1 over 1, so the whole thing is 1. So if you haven't for a while, you might want to go back and remind yourself of all the rules of derivatives, but I'm trying to remind you as you go along, as I did here. So any questions on this? Yet another one. And here I'm actually going to shorten it. In the actual one, there's the third term, but I'm going to leave it shorter. Which is pretty much the same thing, except now we're going to put it together as what's called the gradient again. And remember, the gradient is just the vector that you get when you take all the partial derivatives. So in this case, it's a 2-variable one. If there were 3 variables, we'd have 3 entries and so on. So I said nothing new. So here, what is the gradient? Actually, I'm just going to write it because it's pretty much the same as 1. So the derivative with respect to x, although you will double check me. Actually, write it quicker than I do. And one more, then I'll ask if you want to look at any other ones. And same thing. As I said, this text, he likes using different names for variables. And the reason I put this in, because this is telling you which order we want the partial derivatives. So the derivative of this with respect to e is ln of s. Although and the first one doesn't matter. So it's derivative with respect to z, which is ln of, that's supposed to be an s, minus 2z ln of t. And then the derivative with respect to s. And then the derivative with respect to t. And again, if you think about physics, you kind of understand why we're doing this type of thing. In physics, we know that when we're looking at movement and so on, we break it down by the different directions. So in the direction of x, in the direction of y, and the direction. And so this is kind of a similar thing, which is we're looking at the derivative in the easy directions, which is what's the derivative in the direction of x, in the direction of y, in the direction of z. But eventually, we want to be able to say, well, what if I go in the direction of 1, 1, 1? And we'll be using this to put it together. So the gradient gives us the direction as a vector in each of the basic components. And then we'll talk about how we get it in any other direction. So these are the ones I want to do. It's my usual few. So any other ones from 2.1, sorry, that you want to look at? 34. Second. Okay. So it says the annual gas law is given by this, where P is pressure, V is the volume, N is the number of moles, T is the temperature, and R is a constant. So joules per K times moles. If the pressure is constant, uh, 2,000 pascals, and the volume is held constant. I'm leaving out the units. At 10 cubic meters, what is the instantaneous range of change of the temperature? So find instantaneous rate change T with respect to the number of moles. So from Calc 1, we can do this in one of two ways. One is we can explicitly solve in terms of t and then take the derivative, or we could do it implicitly. I'm going to do the first way, so let me solve it. And here they ask us to find the instantaneous rate of change of t with respect to n, which means we want to get, give me a second. I actually accidentally tapped on a thing and it went off screen, sorry about that. So we want to get the derivative of t with respect to n. We write this, because all the rest of them are just numbers. We're holding those all constant. In particular, I think R is just always a constant. So what is the derivative of that with respect to n? So, constant. And right, so I'll put the negative in front. Derivative of 1 over n is n to the negative 1, so negative n to the negative 2. And we would get a number, unless you really want, I'm going to be lazy and leave it like that. The only little thing is, so once we get a number, is we'll have units. And so therefore the units would be the units of T, which is in kelvins per a mole. So if we increase the number of moles by 1, then the temperature will go down by whatever this number is. So as I said, is it okay if I don't get the number? Any others? Okay, so we mostly did 2.3, but I said don't worry about the homework yet, unless you want to get ahead. So let me start off with just another example or two from 2.3, and then for tomorrow you will be looking at that for homework. And we'll probably also finish 2.4, but we'll get to that. And 2.3, remember, is tangent planes. Which another way of writing it is linearization. So in some ways, the only difference between this question, find the linearization, and find the tangent plane, is going to be in a slight difference in how we write it. All the steps will be the same. So for it, first thing we do is we need the gradient. Or just the two partial derivatives. So the derivative of this with respect to x is, and I'm going to write it one way to remind you that you have to simplify. Right, so this is the derivative with respect to x, which obviously is negative 20x e to the 1 minus x squared minus y squared. That's supposed to be a minus x squared. And then same thing here. And therefore the gradient at 0 is that. The other thing we need is what's the value what's the value of the function itself at 1, 0. So if I plug 1, 0 back into the original function, I get 10. And the linearization or the approximation of the function then is, and you remember that it is the value of the function plus the derivative with respect to x. So it should be a minus, of course. And then x minus the value. So that's the linearization. The only difference between that and the tangent plane is for the tangent plane, instead, on the left, you'd put the z to make it into a three-dimensional object, as opposed to just an approximation. So this is the linearization. The second one would be the tangent plane. And now the point of this, as I said last week, is obsolete, but I could ask you now, get an approximation for the function if we're at the point 1.1 comma 0.2, in which case you'd put in x equals 1.1 and y equals 0.2 and whatever that number would be. Which I'll actually do in a second, one where we get an approximation. But any questions on this is the basic thing, which the basic thing is getting the tangent plane. And again, the idea is similar to Calc 1, which is if we're close to the point 1, 0, then the tangent plane will be close to the surface of the function. So do one more where we actually get an approximation, even though it's obsolete. You don't need to know this, but the volume of a cone is given by that, 1/3 pi r squared times h. So we're going to get an approximation. If the radius is right now 3 feet, so we built a cone that has a radius of 3 feet and height of 5 feet, then how much would the volume change approximately if I instead built one that was 3.1 feet and 5.2 feet? And so like the last one, first step is to get gradient. And here I should be more explicit because it's not obvious which is which. So let me make it r comma h so we know that the first one is r. So what is the gradient of the volume? In particular, try it on your own. And what numbers? 3 and 5. 2/3 pi r h. And 1/3 pi r squared. So at 3 comma 5, it is this is, as always, you're going to double check me. 10 pi and 3 pi. In some ways, we don't need it for this problem. You'll see in a second. But let me actually also get the volume at 3, 5. Therefore, I can say volume at, and I should put the 3 comma 5. Oh, yes, gradient of V, thank you. So 2 people noticed before I did. So that, and then plus the 10 pi r minus 3 and 3 pi h minus 5. But, as I said, for this, I don't really need it. And if I wanted to find the change in V from 3 to 3.1, I plug in the 3.1 and 5.2, get a number, and then subtract off what I get when I get 3. And you'll notice that the 15 pi will get canceled. So I'm going to rewrite it. We have units, we get back units. So I don't really need the full thing, because I know when I'm looking at the change, the 15 pi will cancel, because I'll plug in the 3.1 and 5.2, get the whole equation, and then subtract off what I get when I put in 3.5, which is 15 pi. And so the 15 pi will cancel. Again, this is kind of obsolete, so we won't do too many of them. So any questions on this? I sort of did. Because if I plugged in 3.1 and 5.2, I would get 15 pi plus 10 pi times 0.1 plus 3 pi times 0.2. And then if I plug in 3 and 5, I get 15 pi. So when I subtract, the 15 pi will cancel. So you can either think of it, yes, I plugged in the 2 sets of points and then subtracted, or I realized, well, I can just leave off the value at this, which is the value at 3 comma 5, because I know that's going to go away. So either way of thinking about it. Any other questions? Okay, so move on. To 2.4. And in some ways, this has 2 types of things. One is rules such as what is the gradient of, and that's just a multiplication, not a dot product, of f, the function f times the function g. And you could probably guess, which is, you probably guess that it's similar to the product rule. And you say, oh, I'm going to leave one of them alone, take the derivative of the other one, or the equivalent of the derivative. And I get this rule. So they start with these, and you can do the same thing with dot products, and you can do the same thing with the quotient rule and the chain rule and stuff like that. Similar to this type of stuff in chapter 1, you should be able to do it, but you don't really need to know it. So in the homework, that first set of questions where they're asking you to do something like this, you don't really need to do. The second part sort of starts with this type of thing, which is oh, sorry. So is that the gradient? Oh, yes, that is. This is the gradient sign. Sorry about that. So yeah, in some ways, you shouldn't be worrying about it too much because, as I said, you should be able to do this. So they're talking about differentiation rules for gradients. You should be able to do them, but you're not going to be asked to on a quiz or a test. Second one kind of grows out of this one, which is here we have a function of 3 variables and we have 4 sine of something. We know that to take the derivative, what rule am I going to use? Right, so the chain rule. So I'm going to do 4, take the derivative of sine, leave the inside alone. Take the derivative of the inside. So that in some ways is nothing new. But what happens if we break this up into pieces? So there's an extension of this. Which is the one part of 2.4 that you will need to know, which is there's an extension, which is example if f is a function of, let's just make it 2 variables so it's shorter, and in turn, x and y are themselves functions of other variables. Then if I want to take the partial derivative of f of the innermost ones, what I'm going to do is I'm using a tree type thing, if you've seen trees before, which is I want to take the derivative of f with respect to s. So I take all the paths that will lead me to s. So I can get there by taking the derivative of f with respect to x and then taking the derivative of x with respect to s. Or I can go through y. And if I had another variable, I'd be able to go through that also. So this is an extension of the chain rule. So in one variable, we would just get that first term. Here we have more than one variable, so we can get more than one term. And when I do an example on the next slide, you'll see that in some ways, you can often go back to technique from this one. So if you have all the information, you can sort of get around this. So often what we'll do is make you do it this way by only giving you partial information. Wait. Well, let's do it with an example. It becomes more obvious. Since it's a start, let me make it simple. So here's a function of x and y, and then in turn, x and y are both variables in terms of s and t. And I want to find the derivative of s, and just to be different, let's make it t. So according to what I just did, what we do is all the ways we can get to t, which is I can take the derivative of f with respect to x, which gets me to x, and then I have to take the derivative of x with respect to t, or I can take the derivative with respect to of f with respect to y, and those are all supposed to be partial symbols, and then take the derivative of y with respect to t. So in particular, I would take the derivative of f with respect to x, multiply the derivative of x with respect to t, take the derivative of f with respect to y, and then take the derivative of y with respect to t. And then I might say, well, let's continue. Let's suppose s and t are both 1. Then what's the partial derivative in that case? So I just made it up. This is going to be quite a large number. Should have used some zeros. Because your first step would be, you'd say, well, at point x is 3, and y is equal to 5. So I'd be plugging in x equals 3 and y equals 5, and I get these by just plugging into the functions at the top. I would get 6 times 3 times 5 cubed. Times 3 times 1. I really should do numbers. Oh, this is quite low. Not too bad. So this is the extension of the chain rule. But if you go back to the original thing, you'd say, oh, I don't really need it because I won't do the whole thing. But I can say, well, f is equal to 3 times, well, x is 3st. Y is equal to this. And now I can take the derivative with respect to t kind of in the usual chain rule way. So I don't really need this no rule if I have all the information. I can just plug function into function and see that I really do have a function inside of a function. In this case, you can see I can pretty easily, well, partially simplify it to make it a little bit nicer. But any questions on the idea here? So because what I was saying is what we need to do is look at all the paths you can take to go from f to t. And so I can go through x or I can go through y. but I need to add up all the different paths. So that's why there's the plus in the middle. In general, if you've done combinatorics, usually when you say or, that does lead to plus. So I'm probably getting the language from there because I've done that probably recently. But yeah, I do mean that you want to do the two ways of getting from F to T and then add up all the possible ways. So any other questions on this? Also, as if I had made this simpler, what I could have done, which I usually try to do when I introduce a new concept, is show that in this case we can do it this second way, and we can check, well, do we get the same thing? Which would say that, at least in the abstract, or in this particular case, it is how we would have to do it. Okay. So, as I said, here we have ways of doing it. If we only want you to be able to do it one way, we can give you partial information. Being very repetitive, but that's okay. So I can give you this instead. And I should make it different because I'm not saying that this is the same as the last one. So there's a little something, which is, here I do it, but I will in the next one. There is something we would perhaps have to check. But, so if this is true, then find, and just to be different, let's do the partial derivative of f with respect to s, and s equals t equals 1, which is the only point we can do because that's all the information we have. And so, like the last one, it's that expanded chain rule, derivative of f with respect to x, which is what? So according to the information I've given you, what's the derivative of f with respect to x at s equals t equals 1? Negative 3. And then the derivative of x with respect to t, s, I mean. And then plus the derivative with respect to y, which is the 7, and the derivative of y with respect to t. And then again at 1, 1, which in this case is 28 minus 6. And so I get something like that. So let me do another of these, but where I show that we might have to check something. Let's see if I've messed it up or not. So we have the gradient of f is given by that at the point x, y, z equals 1, 2, 4. If in turn x and y and z are given as functions of s and t, then let's find the derivative of f with respect to s. So pretty much like the last one, just that now there's a quick intro check, which is what has to be true for us to be able to do this problem? And is it? So in other words, can we do this problem? Right. We only know the gradient at the point 1, 2, 4. So if plugging in s equal but I didn't say which order, so I was doing. I have to tell you which is which goes first. X of st. So if s is 0 and t is equal to 2, which is wrong. I have to check. I plug in 2, 0. Do I get the numbers I do? So x at 2, 0 is equal to 1. Y at 2, 0 is equal to 2. Z at 2, 0 is equal to 4. So that's okay. So since you're only given partial information, you can only do the problem if that information gives you everything you need. And what you do then, you just do like the last one, you do the derivative of f with respect to x, which we know is 2 at the point, times the derivative with respect to s, minus 4 times the derivative of y with respect to s, which is at the end there's 2, 0. And then whatever you get. 0 minus the whole thing is 1. And this whole thing is 4. And of course I could do it the other way around. Negative 8. Yeah, you should be checking me, so don't assume it's right, but yes, we get that. So now I'm going to try. So first, any questions on this? Oops. Right. So if we had 10 variables, there would be 10 terms we'd have to add together. So just multiply the partials. Right. So since, as I said, I don't really want to lecture for the whole time, here is just problems for you to work on. So I'm going to give you now try these problems, which I'll also put on Blackboard with the answers after class, and then we'll go over them. So here's some problems from 2, 3, and 2, 4. So before we get to the homework, so for the homework, you're going to look at 2, 3, and 2, 4. So here, let me stop lecturing for a bit, and we're going to go with that. Oh, can you not see? Oh, so right now it's just on screen. So can you see this on screen? Oh, it's hard. Oh, so you should be able to, what I did is, if you go to just to the left, there's something that has a magnifying glass. If you click on it, you should be able to make it look bigger. So let me stop talking here for a minute. I'm going to mute myself. Last time I tried doing in the breakout rooms, I don't think anyone actually used the whiteboards. So let me just leave it like this. You can still talk to each other, but I'm going to stop for a minute. So 10, I'll come back and we'll talk about it. So try it on your own. All right. So I'm not sure if that's not enough time or not. Usually in class I'd be walking around to see where people are, but let's start going through it. I'm feeling kind of bad because I forgot to stop recording it. So let's start as a check, just see if everyone's getting the same thing. Let me go backwards as usual. What do you get for the, oops, I'm waiting. Thing there. What do you get for a number for the derivative of t? Hello? So I guess my first question should be, can you hear me? Can someone hear me? Yes. Okay, yeah, so for from 1, what is the number? So I put this down and someone's going to tell me if they get the same thing. That's supposed to be an 18. Okay, so at least a couple. Okay, what are the units? So someone gave me part of it. Right, so the full thing would be degrees Celsius per meter. So let's go back and get this. So this is just the, and I'll, as I do, leave it without multiplying it out. But of course, you could also do it's negative 18x to the thing. Let's only do the same thing with this one. What do you get for the vector in number 2a? One four. At least a couple, so actually several. So let's assume that's okay. And again, let me kind of double check. So the gradient is a derivative with respect to x. Which is that whole thing, because we need the product rule. And the derivative with respect to y. Yep, so it looks right. And then we also need, so this is the answer to the problem, but for the other one, we also need the next part. What's the value of f at the point 20? And since I'm seeing a tangent plane, I'm going to do z equals, and therefore, what are we getting for the tangent plane? And oops, that's supposed to be a 4. Not sure why I made that a 2. Of course, you don't really need the minus 0. So any questions on those two problems? As I said, after class, I'll scan this. I'll actually write up the answers a little bit nicer in this and put them up on Blackboard. Okay, so again, let me start backwards. What do I get for this? Oh, I'm being silly. Oh, no, I'm not. Well, it shouldn't be a vector. So you get the gradient as 1, 4. But the function itself, so these are not the same. This is the actual answer to part A. This is what's the value of the function at 0, 2, which we're going to then use for the next. And you can see the function is not a vector, so we certainly shouldn't be getting a vector when we plug in numbers. Actually plugging back an original function there. So that's just giving us the first number here. Any other questions on these two? Okay, so this one. So again, as I said, kind of go backwards. What is the vector you get when you plug in 1, 1, 1? See several with that, so let's assume. So let me put in the derivative. So the derivative with respect to x. comma, the derivative with respect to y, derivative with respect to z. And if you put in 1, 1, 1, you get it, the 8, 4, 12. And so finally here, I want to find this. So again, let me go backwards. Z cubed, thank you. Someone get a number for the answer for B, 3B. So everyone's getting 16, so that looks good. So the parts for that are the derivative of f with respect to x, which we know is 8, multiplied by the derivative of x, which is 2, plus the 4 times the 3, plus the 12 times negative 1, which is. So any questions on problem 3? So as I said, I'll write up the answers after class, put them up. Let me now do what I'm going to try to be the usual thing is. So we've done this, and now we're going to quickly start the next section. And obviously, we won't finish it because we have about 15 minutes. But any questions before we move on? So back to whiteboard. I have to remind myself which section we're in, so 2.5. So 2.5 is what I sort of said going when we did the gradients, which is what we want to be able to do is ask, well, what's the derivative in any direction I want? So we have the derivative in the direction of x, or y, or z, the axes. What is it in any other? Sort of a definition. It's more of a notation. So first, a little notation I haven't seen in any other textbooks. In this textbook, he's writing this is the direct derivative, d of subscript of f. Sorry, being silly. Of u of fp. The way you get it is the same in all of them. And as I said, it's kind of the usual physics thing, which is we have the part that's going in the x direction, the part that's going in the y direction, and so on. And then what we'll do is, for the direction we want, we'll multiply that by the piece that's going in the direction of x. And therefore, what we're going to get is the dot product. So if I want to get the direction any of the other direction, what I do is take the dot product. So let me, as usual, start with an example so you can see more exactly what's going on with that. As we do it, I'm going to make it nice and simple so we can do it fairly quickly. So I want to find sort of be a part B. So basically I have two dimensions and I want to find what is the derivative at a 45-degree angle. The first little thing which goes back to chapter 1, is 1, 1 a direction? Yeah, the usual thing. That's 8. Let's see if I can acute. Try to make it different so you can see that where the numbers come from. So yes, is 1, 1, and that's supposed to be a vector. Is that a direction? So 1 point, chapter 1 question. No, because its length isn't 1. So first we have to do is get the direction. So I'll make it a unit vector by dividing by its length. And then the answer is, now we need the gradient. So the gradient of this, as I said, I made is fairly simple. So what did I say, F1, 1, so it's 6, 9. Therefore, our directional derivative is then the dot product of those two vectors. So, as I said, the usual physics thing, we break up it into the x direction, which we do by itself, so we multiply the 1 times the 6. That's the change in the function if we move in the x direction, and then separately say, well, what happens if we then move in the y direction? And then we add the pieces together. So gradient is telling us, so the 1 over square root of 2 is, I'm trying to fit it all in. So the length of 1, 1 is equal to the square root of 1 plus 1. Okay. So here's the basic idea. Looking at this, since this is how we get the directional derivative, it's the dot product of the gradient and the direction. Let me ask kind of a question that goes with it. In which direction is the function going to increase as big as possible? Or in other words, what direction will give us the biggest number here? So let me go to the next page. I might ask it more specifically. So we know the dot product is given by this. I should have known there would be a lag. So that product is as big as possible if they're in the same direction. So as a part B, if I ask, and then I'll put the note. This. It is note. And as someone said, in the direction of the gradient. So here that was problem with not allowing me to save it. Was it 6.9? Is that right? Okay. So therefore, the direction is, now I have to get the length of that, which of course, since I just made it up, is not nice. Uh, 81 plus 36, which is 117 or something like that. Therefore, that's the direction in which the function increases as rapidly as possible. And in some ways, we get, as part of that process, the answer to the second question, in which what is the fastest that the function changes? And that's equal to just the length of the gradient, which we just got, is the 117. So the rate of change in the direction that the function increases most rapidly is the length of the gradient, and the direction is just the gradient divided by its length to make it into a unit vector. So the sort of obvious follow-up, well, that's the direction in which it increases most rapidly. Sorry about the change in the size. In which direction does it decrease most rapidly? Just the opposite. And the rate of change at that point, again, is just the opposite. So any questions? If you've done physics, as I said, this is fairly typical physics. Look at each direction separately and then add them together. So let me continue with, and here this will be a follow-up from the worksheet we just did, which is that, where I gave you that t is equal to this with the units. And the reason I'm using this one is we can then do this fairly quickly because we've done the work, although you'll have to remind me what the numbers are. Actually, I don't think we did the whole thing. In which direction should we move if we're at the point 1, 1, which is what we were in the problem, and we want the temperature to increase most rapidly. So you did part of this which is we need to get the gradient because it's in the direction of the gradient. And this we've already done. I'm not sure why it looks weird, but that's okay. Oh, it wasn't at 1, 1 where we were at. No, it wasn't 1, 1. And so we get this. As I look at it. Which in some ways, if you look at the original function, is what we should expect. Pretty obviously, this function is at a maximum at 0, 0 because we're subtracting squares. So we want to basically move towards the origin, although maybe not directly because the x's increase more rapidly. And then we just have to get the length, which is nothing nice. And in doing so, we also get what is the rate of change. I should sort of put in it, which is what are, since we've already done it, what are the units of this number, which is 6 squared to 10. Right, the same more degrees, so I should really be putting in the degrees Celsius per meter here. So there's the quick introduction to directional derivatives. It actually is pretty much the whole thing, but not really enough to look at the homework yet. So for tomorrow, what you're going to do is look at the homework for 2.3 and 2.4. That's what we'll start with. Okay. Any questions? And obviously, we have to do more examples of this. Okay. So as with last week, I'm going to stop recording, but if you have more individual questions, stick around.